still streaming in virtually, but I think, so it's a pleasure to have Laimei with us, and unfortunately virtually, but nonetheless to have her. And just a very, very brief biography. I mean, so she did her PhD at Stanford with my former advisor as well. So we're sort of academic siblings. And she worked on order and disorder in high-temperature superconductors. And her thesis really focused on many, many different aspects of quench disorder and pneumaticity, and many aspects associated with corporate behaviors. That. Also looking at two-dimensional systems of superfluid Israeli transition disorder, looking at conformal theories. And so she did a vast amount of work in that. And in the last a few years, she also has reached and I think made really deep connections in the thinking about chaos, in particular quantum chaos, and which she'll talk about some of her work today. So I'm really looking forward. So I forgot actually to continue what she actually after she finished her PhD. So after she finished her PhD, she was a Canada Center in Chicago, and then right now she's at Urbana-Champaign. So it's all yours, Laimei.
Okay. Can I start sharing the screen?
Oh, sorry. I think you should be able to. Can you do that?
Yeah, I think so. Minimize this. Okay, can you see my cursor?
Yes, yes.
Okay, good. Yeah, so thank you for the introduction, Zohar, and thank you very much for the invitation. It's a great pleasure to be here, although virtually. And I think I was on campus visiting 3 years ago, pre-COVID. I hope in the future when the things settle down and I get to visit the beautiful campus again. Yeah, so today I will talk about the role of hidden symmetries in defining operator complexity. So I will explain exactly what I mean by the complexity of an operator. But before I move on, let me just say that feel free to interrupt me anytime if you have questions. I know this may not be a topic that is familiar to some of you, but so feel free to interrupt me with questions in the chat or raise your hands or directly speak up. I'm also happy to talk offline. This is my email address if you have more questions or thoughts and ideas. Okay, so you might have heard the word complexity before. So for instance, you might have heard computational complexity in the context of information processing and computer science. So basically, computational complexity refers to how much resource you need to solve a certain type of problem. So a class P problem is only requires polynomial time on a traditional classical computer, for instance. So this is just one example of complexity or one type of complexity. So today we're going to look at another type of complexity called operator complexity. And the idea is that you can quantify how complicated an operator becomes under Heisenberg time evolution, under quantum mechanics. So the complexity of an operator is a tool or is a probe of the property of the quantum dynamics itself. So for example, suppose we have a spin 1/2 chain, okay? And I can label the sites in this way. And suppose at the beginning of time, I have some string of operators like this. So the only non-trivial operator in this string is the sigma z sitting on site 0. And everywhere else I have identity operator. So that's my initial operator. So it's a simple operator. By the way, we usually talk about how time evolves under Schrodinger evolution, but right now we care about operator complexity. So everything will be in terms of operator dynamics and Hilbert space and Heisenberg time evolution. Okay, so now as time goes by, this simple operator will evolve under Heisenberg time evolution like this. And if the dynamics of the spin chain is non-trivial, or to be more precise, if it's quantum chaotic or quantum thermalizing, this operator will become complicated. So I haven't explained exactly what chaos or thermalization means. I will later. But for now, everything is just hand waving. I'm just giving you a picture of how a simple operator may become more complicated under some interesting dynamics. So for instance, this simple operator may become, there will be more sigma z's in the operator string under time evolution. Or there will be superpositions of operator strings as a result of the time evolution. And if you plot the density of non-trivial operators like sigma z or sigma x as a function of lattice site and time, you see that, okay, initially there's only one non-trivial operator, but eventually there will be many, many non-trivial operators under time evolution. So this process of simple operator becoming more complex, or the growth of operator complexity, is a hallmark of the interesting dynamics, or the dynamics that can delocalize quantum information or thermalize it. Okay, so I will.
So can I interrupt? So when you are plotting that thing, you are plotting essentially how is at the range, how many values in the operator, or you also take into account the fact that those linear combinations can grow also exponentially.
Right.
So the two things or only one?
Good. So I'm sweeping some things under the rug now. So this only corresponds to a single operator string. So this plot, it actually doesn't correspond to the case when they are superpositions.
Okay.
So this is just an operator string becoming another operator string, but with more non-trivial operators in it. Yeah, but to be more precise, complex operators refers to not just this operator string becoming a more non-trivial operator string, but rather becoming a superposition of operator strings. Yeah, but this is just a pictorial way of visualizing it, but it's not precise. This doesn't correspond precisely to this superposition. Yeah. Okay, good. So later I will give you a tool of that precisely quantify operator complexity. For now, this is just the physical picture. So let me now mention very briefly why we care about this abstract concept of operator complexity. Well, it's, as I said, it's tightly related to quantum thermalization and quantum chaos. So quantum thermalization refers to the emergence of local thermal behavior in an isolated quantum system. For instance, if I have, this is a collection of cold atoms, cool down to almost zero temperature, right? And I can perform a quantum quench to the system by suddenly change the boundary condition. And I can watch the system equilibrate and settle into a steady state. If you do a local measurement in the steady state, for instance, if I measure how many particles can I detect in this local area on this particular site, I will find a thermal distribution of the probability. So effectively, this local area or this site is in a finite temperature environment, despite the fact that this entire system is in a globally pure state and is isolated from the outside world. So far we don't fully understand how this local thermal behavior can emerge in an isolated quantum system. So that's the mystery of quantum thermalization. A closely related concept is quantum chaos. And we, again, don't fully understand it. We know several important aspects of quantum chaos. For example, sensitivity to initial condition, also known as the quantum butterfly effect, just like in the classical chaos. And operator complexity is supposed to be related to both of them in the sense that for a dynamics to be thermalizing or quantum chaotic, it has to at least have the ability to bring a simple operator to a complicated operator. For instance, bring this local operator sigma z to a more non-local operator. And for the high energy community, they care about operator complexity or growth of operator complexity due to due to black hole physics. Not the classical aspect of black hole, but rather the quantum aspect of black hole. For instance, how can the quantum dynamics of black hole process information so quickly and so efficiently? And the quantum information community care about operator complexity for the sake of building better quantum computers. So this is an example of the Google Sycamore processor. And if you want this processor to function well, then you need those superconducting qubits in the processor to talk to each other coherently. If instead the qubits start to thermalize or to increase operator complexity, then you lose track of the original information you put in the processor. So the quantum information community try really hard to avoid thermalization and avoid the growth of complexity. Okay, so that's a little background and motivation of why we care about operator complexity. So now let me describe a tool that people usually use to quantify operator complexity called the coefficient entropy. And then I will give you an example where the coefficient entropy actually fails. This example is called the quantum cat map with symmetries. And finally, I will give you a solution to the problem. I will propose a new type of tool to quantify operator complexity when they are symmetries. It's called the symmetry-resolved coefficient entropy. Okay, so now let's look at the old tool, the coefficient entropy. So the idea is quite simple. Suppose I have some initial operator O, and it becomes O of t under Heisenberg time evolution. You can expand this O of t using a prefixed operator base, a set of operator bases in your operator Hilbert space, right? And those Cn as a function of time, those are the coefficients. They satisfy this normalization condition. So this expansion is just like expanding your wave function over eigenbases, but here everything is operator. They're not state, they're just operators. Okay, so this tells us that we can treat this coefficient square as probability. And you know, when you see probability, you can define Shannon entropy. So the coefficient entropy is defined as the Shannon entropy of those coefficient square. So mathematically, this is what the coefficient entropy looks like. So it's basically this famous negative P log P formula of Shannon entropy. And what it tells you physically is the uncertainty of this operator O in the operator Hilbert space. So if I do a measurement of O at time t, what's the probability of it landing on a particular operator basis? And that uncertainty can be quantified by this entropy, Shannon entropy, also known as the coefficient entropy. Let me give you two examples. So suppose the operator Hilbert space has dimension d. So the first example is a simple operator, so which has all the coefficients being zero except one term being non-zero. So in this case, this operator, which is basically one basis operator, has coefficient entropy 0. It's extremely simple. If I do a measurement, it 100% will collapse onto this particular basis operator. So it's a simple operator will have 0 or near 0 coefficient entropy. Another example is when the operator has weight that is equally distributed, uniformly distributed over all the possible operator bases. And in this case, the coefficient entropy reaches maximum possible value, log d. So in general, the coefficient entropy can take value between 0 and log of the Hilbert space dimension. Yeah, so that's the basics about coefficient entropy. Okay, and one more thing is, if under a Heisenberg time evolution, under dynamics, a simple operator becomes a maximally complicated one, the coefficient entropy grows from 0 to log d, then we say that this dynamics has maximal growth of complexity. It induces maximal growth of operator complexity. And we think this is a necessary condition for the dynamics to be chaotic or thermalizing. Okay, good. So you may have seen, is there any question?
No, I was going to ask exactly what you're going to say because it's basis dependent.
Yeah, exactly, good. So yeah, so you may have spot some problems with the definition of coefficient entropy. it depends on the choice of basis. If I change to a new set of bases of my operator Hilbert space, then I will get a new value of the coefficient entropy. And the question is, which one should I trust? Which one should I use as a measure of my operator complexity, right? If I choose the wrong one, then it may give me a false diagnosis of the operator complexity and the growth of operator complexity. It may give me the wrong information of how chaotic the dynamics is. So this is a very legitimate concern. And previously, there have been two previous work where the authors claim, especially the second one, where the authors claim that generally, it doesn't really matter what basis you choose. If you just look at the long time saturation value of the coefficient entropy, then no matter what basis you choose, no matter what basis transformation you do, they all should give the same coefficient entropy in the long time limit. And they test this claim in a single particle quantum mechanical model called the quantum cat map. And it worked out. Indeed, we don't need to worry about choice of basis. No matter what basis we choose, we get the same coefficient entropy in the long time limit. So that was nice. However, in this talk, I will show you that this is actually not true. The example they used to test this claim is very specific example. I will give you a counterexample that shows that this claim is wrong. And this counterexample is called quantum cat map with symmetries. Okay, so now this brings us to the next section, which is when coefficient entropy fails. And let me introduce you to our playground, which is the quantum cat map. So let me give you first a brief review of the classical cat map. So it was introduced by Vladimir Arnold, the Russian mathematician. So it's basically for the study of classical chaos. So it's basically a transformation from torus to itself. So I have X and Y coordinate on a torus, and the map is basically the action of this matrix. So, and you get a new pixel on the torus. This matrix has to be a SL2Z matrix, meaning that all the elements are integers and the determinant is 1, so that this map is area preserving. So Arnold first used the picture of a cat to demonstrate the action of the map. That's why it's called a cat map. So I have a picture of cat in the box, which is a torus with boundaries identified. And if you apply this matrix once, the picture will get sheared and stretched. Some of the pixels will go out of the box. So you have to mod it back so that it remains on the torus. And it's a discrete time evolution. So you just keep at each time step, you just keep applying this matrix. And in the end, you get a very chaotic picture of the cat. You don't even recognize this is a picture of cat. And it turns out that this map, when A plus D, the trace of the matrix, is larger than 2, this map will be classically chaotic. It's mathematically proven. So this is just some nice properties and basic information about the classical cat map. And what we are going to talk about first is the first cat map we're going to talk about is this specific one, 2, 1, 3, 2. So all the elements are integers, determinant is 1, and also the trace 2 plus 2, A plus D is larger than 2. So it's classically chaotic. And now let's quantize this. So the quantization of this map was first done by Hannay and Berry. So this Berry is the Berry face Berry, long time ago. And basically the quantization involves 2 parts. The first is the quantization of the Hilbert space or the phase space. The second one is the quantization of the dynamics. So the Hilbert space is basically the Hilbert space of a 1D particle moving on a discrete ring. So it's a periodic boundary condition with discrete lattice sites on this ring. So both, and you can treat X and Y as the position and momentum of this 1D particle. So that's the Hilbert space of the quantum problem. and you can choose a basis for your Hilbert space. So here we choose the basis to be the eigenstates of the position operators. And we have an effective Planck constant from the quantization, which is proportional to 1/n, where n is the number of sites on your ring. And the quantization of the dynamics will give you a n by n unitary matrix. So this is the matrix element. This is the time evolution operator, and these are the states of my Hilbert space. So you don't need to worry about the exact form of this expression. What you need to know is that now we have a quantized dynamics, this n by n unitary matrix, corresponding to the action of this map on the discretized Hilbert space. Okay, so this is all in terms of states, like states and how the matrix element looks like under the states. But we want to translate everything into operator language because we care about operator complexity. So let's see what's the operator Hilbert space and what's the dynamics in the operator Hilbert space. So again, we need to choose a basis. So the basis we choose is this x to the mth power and z to the nth power, where x and z are the shift and clock matrix. They're both n by n. And so this x is called shift because it's identity matrix, but shifted 1. And if you act x on my eigenstate of position, then it shifts to the eigenstate on the next site. And if you act z on the eigenstate, you get just a number. And this number, this omega to the power j, if j is equal to n, the total number of sites, then omega to the power n will be equal to 1. It will go back to 1. So it's like the hours on the clock. That's why z is called a clock matrix. Okay. And x and z satisfy some nice condition, like they're both will be 1 if you raise them to the nth power, and they commute up to some phase vector. And one can expand any operator in the operator Hilbert space using this xmzn basis. Okay, so now let's look at the quantum dynamics on operators. To understand how initial operator O evolves under time evolution, we just need to see how x and z evolve under time evolution. And it turns out the evolution is quite simple. X under one action of the quantum cat map will just become another basis operators. Same with z. So, and this numbers 3, 2, those exponents here are related to the fact that we chose this 2, 1, 3, 2 as our cat map.
Can I interrupt? I mean, the map, if I understood correctly, that you are using at the very beginning, what you call the quantum cat map, quantum mechanically is not well defined exactly because the operator X doesn't exist, okay, quantum mechanically on this ring. So what is well defined is the exponential of those operators, precisely the clock variables you are defining. So if I understand correctly, I mean, these operators and this expansion is well defined, but shouldn't you redefine the quantum cat map in terms of exponentials? Because that is what is the relevant operator. Because in the end, what you are doing when you are doing the evolution in U and U dagger, I believe that you need to include the exponentials of those things. So it needs to be the exponential of these 2, 1, 3, 2, and not the map itself, because quantum mechanically, those operators are not well behaved. You know, there is no Heisenberg uncertainty between Q and P in what you have. So
it turns out that e to the ix, e to the, like if you put x on the exponential, that corresponds to P because, that corresponds to P, I think.
Right, but what I'm saying is that this Q vector you have here, these are not the same as the Qs, which are the eigenstates of the Q and P. These Qs are the clock, okay, the exponential. These are the eigenvectors of the exponential, but they are not the eigenvectors of the Q operator. Because the Q operator is not well defined.
I see. I
You
see.
see what I'm saying? The Q operator is not well defined. So these are not the Q eigenvector. I mean, the ket Qj plus 1 or Qj are not the eigenvectors of the Q operator. These are the eigenvectors of the exponentials of these operators you're writing here. I mean, there is a shift and there is, you know, the clock. So the clock Z, these are the eigenvectors of Z, which are phases.
Right.
And the other is the shift. It's like the Fourier transform.
I see. So you're saying, but this is correct.
Yeah. This is completely correct. What I'm saying is that I think that you need to modify the quantum cut map to be well defined in the exponentials and not in Q and P. That's what I'm trying to say.
Q and I see what you mean. Yeah.
I think this map is not well defined quantum mechanically. That's what I'm trying to say.
I think there is a way to use not the Q but exponential of Q's to define quantum cat map. There is such a way. Yeah.
Exactly, and I think that this is the right quantum cat map quantum mechanically. Is that one? It's not.
Yeah. But for our discussion, I don't think it really matters.
Well, no. I'm just trying to understand what you're doing. Of course, if you continue working with the exponentials, it's fine. You save the date.
Exponential of what?
I'm saying if you work with the exponential maps, because you're using the clock variables, that's correct. That is kinematically correct. All I am saying is that the map itself that you wrote is not well defined quantum mechanically.
Oh, you mean the
exponential of that map that is defined quantum mechanically correctly. That's all I'm saying.
When you say exponential of the map, do you mean the time evolution operator?
The exponential of the map I mean is e to the I alpha q, and e to the I beta, let's say, p. This is well defined.
Yeah, so I think I don't fully understand when you say exponential.
Okay, but I will ask you here, where is your matrix 2, 1, 3, 2? Where is that matrix? Here, in this quantized dynamic, where it is written?
2, 1, 3, 2, in the end, it turns out to be those exponents.
Turns out to be what?
Those exponents.
Exactly. It's going to be related to the exponent. That's what I'm saying. So in that regard, in that regard, what you are using in the end is the exponential map.
Yes.
Quantum lines, you're using the exponential map and not the map you wrote before. So
right. So, exactly. So it's not exactly this one. It's just that I can find a quantized n by n matrix which is related or is derived from this.
Exactly. Yeah. The right map is exponential one, is not this one. That's all I'm saying.
Okay, now I see what you mean. Yeah. But we're good. Like there's no inconsistency. Everything is well defined. Yeah.
No, what you're doing afterwards is perfectly well defined.
Yeah, good. Yeah, thanks for the clarification. But everything should be consistent and good. So what I was talking about is, so we were here, I think. So I was talking about the dynamics in the operator Hilbert space, right? So to understand the dynamics, how U acts on the operator, we just need to understand how U acts on the X and Z. And it turns out that it's not doing anything fancy. It's just turns X into another basis, turns Z into another basis. And in general, for any given operator basis, if you keep applying this quantum cat map dynamics, it will just turns it into another operator basis. So quantum cat map only reshuffles the operator basis. So that already feels like a very simple dynamics. And we can further study or verify our intuition of this simple dynamics by looking at the coefficient entropy. So suppose I choose a simple operator, like it's just one of the operator bases at time t0, and I time evolve it using Heisenberg time evolution. So here I'm plotting the coefficient square as a function of m and n in the operator Hilbert space. So at the beginning, all the weight is on one operator basis. As time goes by, you see that this weight just jumps around. It never gets redistributed. And if you compute the coefficient entropy, it's 0 at all times. So that means this quantum cat map does not induce growth of operator complexity at all. That's very interesting because we said that operator growth or operator complexity growth should be a necessary condition for quantum chaos and quantum thermalization. This just means that quantum cat map is not chaotic. Although the classical cat map is chaotic, it's classically chaotic. And this observation from coefficient entropy is in agreement with observation from other diagnostics of chaos. For instance, I'm plotting the level statistics. So level statistics is obtained by first diagonalizing the time evolution operator, obtain all the eigenvalues, and you collect all the nearest neighbor level spacings. And you plot a histogram of those level spacings. So you see that you have the huge probability of finding 0 level spacing or a very small level spacing, meaning that the levels love to cluster. They like to be near each other or to be degenerate. And this absence of level repulsion is a hallmark of a non-chaotic system. So this Poisson shape, huge probability at 0 level spacing, this Poisson distribution means that quantum cat map is not chaotic, which agrees with our observation from coefficient entropy, that a simple operator remains simple as time goes by. Okay, so let's look at a more complicated case. It's called the perturbed quantum cat map. So I'm adding an additional term here. It's a shear term. And you don't need to worry about the specific form of the shear term. You just need to know that overall, this entire map is still area preserving. Also, this kappa, the perturbation strength, does not have to be small. We call it perturbation, but it doesn't have to be small. And we can quantize it. For instance, again, we choose 2132. And so after the quantization, the operator Hilbert space is the same as before, spanned by this operator basis. And the quantized dynamics will change because of the shear term. So this is what the matrix element of the time evolution operator looks like. So we have the original cat map and additional term induced by the shear. So it's proportional to kappa. And in terms of the action of time evolution on X and Z, now X will change into a superposition of operator basis, same with Z. So this seems like a more complicated dynamics. Compare with the original non-perturbed quantum cat map, where X just turns into another operator basis without superposition of all the operator bases, and same with Z. Okay, so and we can actually quantify this more complicated dynamics using the coefficient entropy, or people have quantified it using coefficient entropy. So let's again choose a simple operator and time evolve it using the time evolution corresponding to this perturbed quantum cat map. So again, I'm plotting the coefficient square as a function of m and n, and you see that this originally concentrated weight will start to spread out as time goes by. And eventually, this time evolved simple operator will become very complicated operator in the sense that it will have support over all the operator bases in the entire Hilbert space. So this is what the coefficient entropy looks like as a function of time. It starts as 0, it's a simple operator, but eventually grows and saturates to the maximal possible value, log n square, where n square is the dimension of the operator Hilbert space. Okay, so this tells us that this perturbed quantum cat map has maximal growth of operator complexity. It brings a simple operator to the maximally possible complicated operator. And this observation is in agreement with level statistics. So again, this is a histogram of nearest neighbor level spacing. And this particular shape is called Wigner-Dyson distribution. And in contrast with the previous Poisson distribution, Wigner-Dyson has a 0 or very small possibility of finding levels near each other. So levels repel, and that's a hallmark of a chaotic system, interacting chaotic system. So this, our observation from coefficient entropy agrees with level statistics.
May I ask a quick question on the previous slide before this one? Before this slide, there was another one with the picture of the spread. Yeah, yes. The spreading, right, of those ridges there, are those along the eigenvector of the matrix, or is related to the shear? Do you know what those lines represent?
Oh, yes. I think these are due to some number theoretic property, very like unique to this matrix.
Because the matrix is stretching along the eigenvector, right? Could that be, or do you think it's related to the shear? It could also be the shear, because it wasn't present in the actual.
It wasn't present if you don't have kappa. That's right. But I think, how should I explain it? It will be there if kappa, even if kappa is very, very small. Yeah. And the specific stripe pattern is due to this specific choice 2132.
I see. That's interesting.
Yeah.
Yeah. Thank you.
Yeah. Okay.
So
good.
infinitesimally, so even with an infinitesimal kappa, you have maximal growth.
Yes, it will just be slower, but it will eventually reach the maximum possible value. Yes. Yeah. Okay, good. So, and then comes to the question of whether we should worry about basis dependency. Well, the authors found that, at least in this example, we don't need to. So this is the coefficient entropy as a function of time for this basis. If I choose another basis, if I do a basis transformation, you see that, okay, the early time behavior of coefficient entropy will be different, but in the long time limit, things don't change. So they both gave the same value of coefficient entropy, this maximal possible value. So in this sense, at least in this case, it really doesn't matter what basis we use, as long as we only look at the long time limit. So that's all good. However, as I mentioned before, there are counterexamples to this claim. So the counterexample is the perturbed quantum cat map with symmetries. So this is the generic form of the perturbed quantum cat map. And the claim is that when B is not 1, and also when n, this quantization parameter, when n is a multiple of B, there will be additional symmetry in the quantum cat map. And previously, B is 1, we have 2, 1, 3, 2. So the symmetry isn't there. But right now, if we consider a generic case, when B is not 1, you may have quantum symmetry when n is a multiple of B. So what is the symmetry? Well, classically, you can do a shift or change of momentum. Let's call the matrix, classical matrix W. If you add W on Q and P, what it does is it increase P by 1 over B. There exists such operation classically, okay? And my claim is that W can be quantized and becomes a symmetry of the quantum cat map if and only if n is a multiple of B and when B is not 1. So why is that? Let me give you an example. Suppose B is 13. I just randomly choose number 13. So this is 13 and n is a multiple of B, 130. Okay. In this case, this change of momentum 1 over B is 10 times the lattice constant. So this 1 over 130, this 1 over n, is the lattice constant in my discretized Hilbert space. So the shift of change of momentum is integer multiple of the lattice constant. So the new momentum after the shift will remain on the lattice site. That's why it can be W can be quantized. If n is not a multiple of 13, then the new momentum will not remain on the lattice side, and W cannot be quantized. So that's why you need this condition of N being a multiple of B. And this symmetry is the change of shift of momentum. And mathematically, the difference between 2, 1, 3, 2, or for instance, when B is 13, I can cook up matrix ABCD as this one, 14, 13, 15, 13. So this is a legitimate SL2Z matrix, and it can give us a quantum cat map, but this cat map will have additional symmetry compared to this one. Mathematically, because for this one, if you remember, we will have the time evolution operator looking like this. I have this original cat map term and the shear term. But for this guy, it will become more complicated. So you don't need to worry about the details. You just need to know that this comes from the original cat map. This is the shear kappa. And there will be additional Gauss sum function, this G function, just at the end of this expression. And it's related to the greatest common divisor between N and 13, B equals to 13. So this G function won't be there if B is 1. The greatest common divisor between N and 1 is 1, so G will disappear. But because B is now not 1, and when N is multiple of 13, this G function will have non-trivial contribution to my time evolution operator, and that will contribute, that leading to the existence of symmetry. So this is just the mathematical side of things. But now let's forget about mathematics and go back to the physics discussion. So what does the quantum symmetry look like? So what is this W after you quantize it? Well, it's basically this guy, where Z is the clock operator. So it's a diagonal, Z is diagonal, so W is also diagonal. And because the W and U, my time evolution operator, commute, my time evolution operator now can be block diagonalized due to the existence of the symmetry. And the block diagonalized structure is like this. So we have B blocks, equal sized blocks. So for instance, for B equals to 13, this 14, so A, B, C, D are 14, 13, 15, 14. So if that's my choice of matrix, then if I choose N to be a multiple of B, then there will be 13 blocks of in the block diagonalized structure of my time evolution operator. And each block will be of size 10 by 10. That's just because of the existence of this symmetry, W. Okay, so that's the counterexample, and let's see how it acts against coefficient entropy. Oh, one more thing, yeah. So before I go to the coefficient entropy of, in this case, let me just quickly mention the level statistics. So the level statistics of this perturbed quantum cat map with symmetries will look Poisson-like. Meaning that there will be a lot of levels clustered together or be degenerate with each other, and it's not chaotic. And the reason it's Poisson-like is because it comes from the sum of independent Wigner-Dysons. So in this case, it comes from sum of 13 Wigner-Dyson distribution. So if you sum together independent Wigner-Dyson distribution, you will get a Poisson distribution. Each Wigner-Dyson distribution, each sub-block is fully chaotic because it's Wigner-Dyson. But if you sum up them together, you will get a seemingly non-chaotic model. And that's agreeing with our intuition, because you have symmetry. If you look at the entire 130 by 130 matrix, it has symmetry. Once you have symmetry, you cannot be fully chaotic. And the more symmetries you have, the more integrable your system will become. So it makes sense that if you have just one symmetry, your level statistics will become Poisson. It will not be Wigner-Dyson anymore. Okay, so that's about the this counterexample, perturbed quantum cat map with symmetries and how level statistics look like. So we know from level statistics that this model shouldn't be fully chaotic. Now let's look at what coefficient entropy says. So coefficient entropy, again, let me choose a simple operator and compute the coefficient entropy under a randomly chosen basis. So this is my original basis, but I'm doing a basis transformation. R is a randomly chosen unitary matrix. So this is a generic choice of basis. And you see that it saturates to the maximal possible value. So it's fully chaotic, or at least it's maximally operator complexity growth. It contradicts with what we saw in the last slide about with level statistics. It shouldn't be fully chaotic. On the other hand, if we use the old choice of operators, operator basis, it will saturate to a significantly smaller value than the maximum possible value. So if we are lucky enough to choose this operator basis and measure coefficient entropy under this set of bases, then we will be able to see that this perturbed quantum cat map is not fully chaotic. But in general, we don't have such luck. In general, we usually just randomly pick a set of bases and measure coefficient entropy. And if we see it's saturating the maximal possible value, we will say, oh, it's very likely fully chaotic, but it's actually not. So this is the example where coefficient entropy for a generic choice of basis fails. It falsely tells you the system is fully chaotic, but actually it's not. And this brings us to the last part of the talk, which is a solution to this dilemma. So I will propose a modified version of coefficient entropy called symmetry-resolved coefficient entropy, so that we can better quantify operator complexity when they are symmetries. So we know that when they are symmetries, especially hidden or unknown symmetries, the Hamiltonian or the time evolution operator should be secretly block diagonal. So it should be something like this. The blocks don't have to be equal size. And what we need to do is not to consider the dynamics within the entire matrix, but instead we should zoom in to one symmetry block. We should mod out the symmetry and just look at one symmetry block. And we can study operator dynamics and operator coefficient entropy within that symmetry block. So for instance, I can do the expansion of an operator. This operator is of smaller size using basis operators of a smaller size, and I can get coefficient and the coefficient entropy just within that constrained to that one symmetry block. So this is the symmetry-resolved coefficient entropy. So the idea is very simple, right? So because the existence of symmetry ruins the validity of coefficient entropy, now let's just mod out the symmetry and look at coefficient entropy within one symmetry block. So that's the symmetry-resolved version. It sounds simple, but the hard part is, how do you find the block diagonal structure of a Hamiltonian without knowing the symmetry? How do you do that? How can you do that? Well, the answer is yes, you actually can do that. So there's a very nice numerical scheme developed by people actually at UIUC, and they were developing it for the sake of studying spin liquid. Their motivation was completely different from ours, but it turns out that their numerical techniques is applicable to our case as well. So basically, next, I will tell you how to identify symmetry blocks of a Hamiltonian without knowing explicitly the symmetry. Okay, so let's consider some general recipe. Suppose I have a Hamiltonian or some time evolution operator that consists of H1 and H2. So you can treat H2 as the perturbation and epsilon is a perturbation strength. And this Hamiltonian has a symmetry, P, that commutes with both H1 and H2. Or equivalently, this Hamiltonian commute with P at any epsilon. Okay, so we say that this symmetry P is a robust symmetry in the sense that itself does not depend on epsilon. It also commutes with H at any perturbation strength epsilon. Okay, so this is our prerequisite. And now we ask if we can block diagonalize H epsilon. If we know what P is, then things are easy. Just giving you a Hamiltonian and you know exactly what the symmetry is, and we ask you to block diagonalize a Hamiltonian. That's simple. That's very basic linear algebra. So what you do is, first step, you find the eigenstates of H1, and suppose they are non-degenerate. If the eigenstates of H1 are degenerate, then you redefine H1 basically by borrowing something from here. And you can always find eigenstates that are non-degenerate. Okay, so using those eigenstates, I can, because H1 and P commute, I can use the eigenstates of H1 to diagonalize P. So P will look like this under the eigenstates of H1. So there will be degeneracies in the eigenvalues of P, so not all the same degenerate eigenvalues will be grouped together, but it will be diagonalized. Okay, and the second step is we reshuffle those eigenstates of H1 into, just reshuffle, we are not doing linear superposition, just reshuffle them into a new set of eigenstates so that all the same eigenvalues of P will be grouped together. Okay, so right now this P is still a diagonalized form, but it looks better because all the same eigenvalues are grouped together. And from the knowledge of linear algebra, we will know that under this new set of bases, H2 will also be block diagonalized because H2 commute with P. So we're basically using P as an intermediate media to block diagonalize H1 and H2 simultaneously. So this is the easy case when we know exactly what P is. Okay, so now let's talk about the more realistic case when we don't know what P is. We know what Hamiltonian is, and we assume there will be a hidden symmetry of the Hamiltonian. That is a robust symmetry that commutes with both parts of the Hamiltonian. But we don't know exactly what it is. So the question is, can we block diagonalize the Hamiltonian? Well, the answer is yes, you can do that, but with some detour. So the first step is, again, find the eigenstates of H1. Suppose they're non-degenerate. And then you need to compute H2 under this eigenstates. Basically, you need to compute this matrix element. So this is H1's eigenstates, and you just compute this matrix element. It's either non-zero or zero. If it's not zero, then it means psi I and psi j, those H1's eigenstates, belong to the same symmetry subspace of P. This is just from linear algebra. You may not understand it on the fly, but it's from linear algebra, based on the fact that H1 commute with P and H2 commute with P. And if this matrix element is zero, then those two eigenstates of H1 live in different symmetry subspace, different symmetry blocks of P. And this matrix is the H2 under the states of eigenstates of H1 is basically an adjacency matrix of an undirected graph. So what do I mean by that? It means that, so here is a graph consisted of points and lines connecting the points. So the points represent the different eigenstates. And if I draw a line between them, that means they are connected by H2. And it also means they live in the same subspace, symmetry subspace of P. So the next step is to find the connected components of this adjacency matrix, or equivalently, find the connected cluster or symmetry subspace, which is, for instance, in this graph, those 4 points are connected, meaning that those states represented by those 4 points will be living in the same subspace of symmetry P. And how to find the connected components of adjacency matrix? Well, that is a very well-solved, well-known problem in graph theory, numerical graph theory. So there is an algorithm doing that. Once you find the connected components of adjacency matrix, that means you've already shuffled your original states into some new eigenstates. And this set of new states will be your tool. So if you rewrite H2 under those new eigenstates, it will be block diagonal. H1 will also be block diagonal. And H epsilon, your original total Hamiltonian, under this new set of states will also be block diagonal. So this is the numerical procedure that Brian Clark et al. Developed to block diagonal a Hamiltonian without knowing explicitly what the hidden symmetry is. So the extra step you need to take is to compute this adjacency matrix and find the connected components of the adjacency matrix. So this is all very technical, but I just want to show you and let you know that just based on linear algebra, we have a numerical procedure to find the block diagonal structure of a Hamiltonian or a time evolution operator, even without knowing explicitly what the symmetries are.
Can I ask a question?
Sure.
So you are saying you don't know what the symmetry P is, but you are guaranteed that it commutes with H1 and H2. So that information you know, because if you do not know that it commutes with H1 and H2, you cannot do this.
That's right. So if I have a Hamiltonian that doesn't have a symmetry like this, and if I just brute forcefully close my eyes and follow the numerical recipe, it will fail. You will not get a block diagonal structure in the end. And you know at that point that, oh, the Hamiltonian doesn't have such symmetry. If a Hamiltonian turns out can be numerically block diagonalized following this recipe, then you know that there is some hidden symmetry. Although from the beginning to end, you never use the explicit form of the symmetry and you don't even know the existence. Yeah, and so it's like, yeah.
But there is another situation that can happen. That is that you have a symmetry that is a symmetry of a subspace of your Hamiltonian, which is not in the full spectrum, okay? So it may happen that some projection over some set of states of that Hamiltonian has a symmetry, but is not a symmetry of the full spectrum.
Right.
And, you know, doing this, you are not going to discover that hidden symmetry. I mean, let me give you an example of that. Suppose you have the TJC model, okay? The TJC model has embedded a symmetry that is the XXC symmetry, okay? It's a quantum symmetry. It's embedded, but it's embedded in the ground subspace, okay? The full spectrum of that model doesn't have that symmetry, that quantum symmetry, but if you project that Hamiltonian to a particular subspace, then there is a hidden symmetry.
Mm-hmm.
You see what I mean? So there are several hidden symmetries which are subtle, that are essentially only acting on subspaces.
Yeah.
You agree with me, Soha, right?
Yeah, of course, emergent symmetries. Actually, I really, absolutely. Actually, I really apologize. I mean, so I guess I started a bit late. So if you can sort of say, because it's been an hour. So if you can, like, in the next few minutes.
Yes. Oops.
But if you can sort of say the essentials, it's of course online, so it's easier for people to read if you want to. But
yeah,
just as,
yeah, this will be ending soon. Yeah. Yeah. So for Gerardo's question, I think it's a really good reminder. This method, I'm not sure. I think it probably won't treat that kind of subspace symmetry. I haven't thought about it. But in terms of chaos or thermalization, how much role does those subspace symmetry play? We also don't know. So that's a good question. Yeah. Okay, so yeah, let me just quickly show you how this general recipe works in the perturbed quantum cat map with symmetries. So basically, we identify that, okay, so this is my time evolution operator, and it can be split into the original cat map and the shear times the shear. And this kappa, the perturbation strength here, plays the role of epsilon, and the shear plays the role of H2 of the perturbation Hamiltonian. And we need to check two things. One is if we follow the numerical procedure, the time evolution operator can be numerically block diagonalized. And if the block structure is consistent with what we know explicitly about the symmetry, the shift of momentum. So we basically pretend not knowing the symmetry and we just follow the numerical procedure. And we want to check consistency with the explicit form of the momentum. And the second thing we need to check is if we zoom into each symmetric block, what's the level of statistics and what's the symmetry-resolved coefficient entropy. And in particular, we know that there is no more symmetry within each symmetric block. This is the only one symmetry of the system. So if we zoom into each symmetric block, we should have full chaos within that symmetry subspace. We should have Wigner-Dyson level statistics, and the symmetry-resolved coefficient entropy should saturate the maximum possible value. Yeah, so those are the things we need to check. The first thing, the blocks diagonalized structure is easy to check. Indeed, we follow the numerical procedure and we found that there will be 13 blocks and equal size. The second thing is, okay, so let's first check the level statistics. So here is the example of that 14, 13, 15, 14 map. And I choose n to be 3003, which is a multiple of 13. So now we have 13 blocks and each block is of size 231 by 231. So let me plot the level statistics and you see this Wigner-Dyson shape. It's not ideal Wigner-Dyson because of the 231 is still a small number. You need more energy levels to have a better plot, but we are satisfied. It's not Poisson anymore. Okay, good. So this is checked. And finally, this is the coefficient entropy, symmetry-resolved coefficient entropy within each symmetric block as a function of time. I hope you can see the two different lines. So the blue line is plotted under the old choice of operators. The red line is plotted and you see that in the late time they are the same. And they're both very close to the maximally possible value set by the Hilbert space dimension of my subspace, symmetry subspace. So in this sense, within each symmetric block, it's fully chaotic. The simple operator will become maximally possible complicated under time evolution. Okay, so with that, I would like to quickly summarize what we have done. So I give you a precise tool or old tool that people use to quantify operator complexity. That is the coefficient entropy. It's the Shannon entropy of operator coefficients. And we see that it fails in the quantum cat map with symmetries. And we further propose a symmetry-resolved coefficient entropy as the proper diagnosis of the operator complexity. And in particular, I told you how to block diagonalize Hamiltonian without knowing the symmetries using a numerical procedure developed by the spin liquid community. And we apply this general recipe to the perturbed cat map with symmetries and saw its success and effectiveness. So in the last 1 minute, let me just briefly mention what's lying ahead of us. So in this talk, I give you some general description of coefficient entropy and operator complexity, but the examples I talk about are all quantum cat maps. So it's a single particle quantum mechanical systems. So you may ask, what will happen in many-body system? Can we study operator complexity in many-body system? Well, the answer is yes. So people have studied something similar to coefficient entropy in many-body system. But now the question is, those studies also suffer or may also suffer from the problem of basis dependency, especially when they are symmetries. So it would be interesting to look at symmetry-resolved coefficient entropy in many-body systems. So for instance, the typical examples we can look at is the interacting integrable systems, which are interacting, so they look chaotic, but they have extensive amount of secret symmetries. So they are integrable in the end. So it'd be interesting to apply our schemes to those kind of systems. And finally, this is a kind of a zoo of tools that people use to study quantum thermalization or quantum chaos. And we talk about a corner of this map, which is complexity or operator complexity. There are many other things. For instance, you may have heard of eigenstate thermalization hypotheses, blah, blah, blah. And the arrow means that there are some connection between those diagnostics. It doesn't mean they are equivalent. It just means they are related. But of this zoo of diagnostics, no one knows exactly what is the fundamental description or fundamental picture of quantum thermalization and quantum chaos. They are all necessary, but not sufficient condition for diagnosing quantum chaos and quantum thermalization. So I think a fundamental question in the field is to look for the universal and precise formalism. And my approach to this question is to start from math, which is dynamical system. This is basically the math description of classical chaos. There are many interesting concepts from this that we can borrow and translate into the physics context. And if you're interested in this, I'm happy to talk about it offline as well. So with that, I'd like to end my talk and take more questions if there is any.
Thank you, Laimei. It was a fantastic talk, and I'm sorry for rushing you.
Yes, no worries.
Beautiful. So, any additional questions?
Yeah, I have one question about the separation of H1 and H2.
Mm-hmm. Yeah.
Is there any physical understanding what should H2 be? Since you said if H1 doesn't work, we can take some part of H2 and mix it up with H1.
Yeah.
That is number one. And second question related to that is, does H2 have to be of the same form, like you call the clock operator or something?
Sorry, does the H2 have to be
the form cosine something or?
Oh, no. So good question. So let me answer your first one. In general, H doesn't have to be separated in this way. As long as H depends on the parameter epsilon, I can always choose an H1 that is H at epsilon 1. Let me just define that thing as H1. And I can find the eigenstates of that H at epsilon 1. And then H2 is defined as H at epsilon 2. Yeah, in general, I can do that. I don't need to explicitly split the Hamiltonian into this way. So just replace this H1 by H at epsilon 1. Replace this H2 as H at epsilon 2. And we're good. Yeah. So that's the answer to the first question. And the second question about explicit form of H1, no, it doesn't have to be cosine, those kind of things. This is a very generic recipe. It should be very generic. Like this recipe was applied to the spin liquid literature, spin liquid Hamiltonian, or possible Hamiltonian model for spin liquid. So there, it definitely is not. The Hamiltonian will look nothing like the quantum cat map, but still this general recipe works out. So
thank you.
I mean, there were some questions. I mean, I want to ask a question, but I think there were others. There are no questions so far. Can I ask a question?
Go ahead, Roger. Absolutely.
So, I think that the important thing about thermalization, because in the end, what you're after is thermalization. I mean, that's a real, a real thing that you're after. When you're after thermalization, I think that part of the problem is, what do you mean really by thermalization? Because I think that when you start having now many degrees of freedom, you have a many-body system, as you're saying.
Mhm.
It will be strongly dependent on how is that you deal with your many-body system. That is, how is that you make, if you want mathematically, what I mean is, how is that you make the tensor product the composition of your system? Okay, so, or if there is a tensor product, maybe there is a subspace of the tensor product decomposition. But it will depend, anything that you are trying to answer should depend on that. And then the question is this: how do you define thermalization? And I think that the physical definition of thermalization will depend on what's the instrument that you use to measure and to decide whether something has been thermalized. You know, whether you're putting a thermometer here or you're using whatever measurement that determines whether something is thermalized or not. In my opinion, I mean, I don't work in thermalization, okay? Let me start from there, but I've been following some of the talks, okay? And I think in the end will depend on the relation between the instrument that you use to say that something is thermalized, and there should be a direct relation between that instrument and the particular tensor product decomposition or whatever the composition of your Hilbert space. And it's that relation that will depend on that. This is a relative concept. You see what I'm trying to say? It's going to be a relative concept. It's not going to be an absolute concept. So what do you think about that? I'm not an expert on that, but I have, you know, like my thinking of the thing. So what do you say about that?
So when you say instrument, or the things to measure, that the quantities that we can measure that come into my mind is, for instance, like number of particles per site, as the example I showed at the beginning, and also entanglement of a subsystem, right? So it turns out
Entanglement is relative, but the entanglement is relative. That's the point.
Sorry?
Entanglement is relative, either to a particular tensor product composition. Let's say if you have a tensor product Hilbert space, it's either depending on the particular tensor product decomposition, or, that is the way I like the best, is with respect to the algebra of observables. Okay, so it's not general. That concept is not general. That's the reason why I'm saying that depending on how you define entanglement, I think that there should be a different notion of what it means to be thermalized. So, I mean, within this framework I'm talking about. Okay?
Yeah, but
there is another framework.
Yeah, but at least as far as I know, the thermalization, defining thermalization using entanglement does not just require how one entanglement behaves. It's like all the entanglements of all the subsystems of size 1/2 of your total system should obey some thermal relation. So it's not just one system. It's a very strong condition that requires a lot.
Yeah, but this involves a measure. That involves a measure of entanglement. You know, yeah. Whenever you are defining entanglement, even if you are separating half of your system, okay, at that moment, you're already decided for something. What it is, real space. So you say, take my system, I do half. That is already an assumption, okay, on how you are going to define, which is okay, because if you're in a lab and I am having my system here, I know it's here, okay, I'm an observer and real space makes sense.
Yeah, I agree.
Okay, yeah. But then I'm saying there are other things, even if you do that, there are other things that even in your half part that you decided to choose, that may depend on the relation between the instrument that you are using to make a measurement and the way you have decomposed your system within that volume or sub-volume. That's what I am trying to say.
Yeah, so maybe an example.
Let me just interrupt for a moment. I have to rush out, but I enjoyed your talk. It was very nice talking to you before. Hope to see you again at some point. Bye.
See you. So sorry. I mean, if someone wants to ask question, I mean, I want to stop asking questions.
Yeah.
But
So maybe an example of what you're saying is maybe a system thermalized in real space, but not in momentum space, or vice versa. Is that?
for example, this could be an example, or another example could be, you know, I have a system that thermalizes, for example, in the language that you're using now that you talk about number of particles, where that thermalizes in a particular observable that is a local observable, like the number of particles per side, per whatever that you want to define, or some other observable that is longer range, when you know is perhaps, you know, involving something else than local observables. Okay, that's another way of saying the same thing I'm saying. Okay, so that concept is relative to that. And what I'm trying to say is that from this perspective, I think that this notion of thermalization will be depending on that relation. It cannot be independent. It's quantum mechanics. I mean, quantum mechanics depends on that.
Yeah, so I'm not saying that there will be just one, like just one version of thermalization. As you're right, like there may be some case-based thermalization instead of real space thermalization. But I would say that right now, since we live in the real space, a natural choice to look at the reference, natural choice of reference space is the real space. And of course, by saying that, I'm not including the thermalization in case-based. That's a very good question. But if you just restrain yourself to real space, then a lot of things like delocalization of information or propagation of entanglement of information, that becomes natural. And within this real space framework, I think there should be, or we are heading towards a universal formalism. But of course, then you have to talk about what's the relation with case-based thermalization, for instance. Yeah, that's a good question. But if we think that we live in real space, and when we talk about local excitation, we refer to local excitation in real space, then there should be one universal formalism. Or I shouldn't say there should be, or we are trying to find the universal formalism. It may not exist, but we're trying to find it. Yeah. Yeah, that's a valid concern. I think the pending question in the field is that we don't have a clear, we have all kinds of empirical tools as listed here of describing different aspects of thermalization or chaos, but we don't have a unified language or tool to.
Yeah, don't get me wrong. I mean, I think it's fascinating. This is not. I think I am trying just to understand better. Okay, because I think that in the end, what is going to be fundamental is going to be the connection to, you know, to real experiments.
Yeah, and also
and you go there, and you can get lots of fantastic insight, you know, on you know, many localization, I mean, or whatever, okay, that you want to use, and maybe even create something new. I don't know. I have no clue. But yeah, I mean, so I'm trying to say it's not that I'm just trying to get, you know, your thinking about the subject. That's the reason why I'm asking in this way.
Since you mentioned experiments, as far as I know, so far, all the experiments regarding quantum thermalization are done within the framework of real experiments. Like they measure cold atoms, as I mentioned at the beginning. You do a quantum quench to the cold atom system, and you measure just in real space locally how those local properties change or relax or thermalize. It's all within local space in cold atom experiments.
No, I understand. That's
yeah, it's the only place where you can go to large system size or like thousands of particles. You can probably do case-based thermalization in a, I don't know, trapped ion, like a few trapped ion quantum computer or a few superconducting qubits, not as many as cold atoms. So far, I think the major many-body thermalization evidence come from cold atom, and it's in cold atom we can do. I think it's all real space experiments, either entanglement measurement or like local physical property measurement. Yeah. So maybe in the future people will start doing case-based or yeah. So
yeah, but even in the case, you know, even in the case of ion traps, for example,
Mhm.
Even in the case of ion traps, when you're thinking about, I don't know, let's say 100 ions, 50 ions, whatever, there are many more degrees of freedom which are there. Okay, you have all the, you know, all these collective phonon modes that, you know, you get from this Coulomb system, and you get all these things which are, you know, essentially degrees of freedom that are interacting with, you know, what you believe is this quantum degree of freedom that you are looking at. So even there, I mean, I think that people will, or I mean, they already started, but I'm saying people will look at this kind of thermalization because, of course, it's an interesting question. I mean, no doubt about it.
Yeah. Another way of verifying thermalization is to look at numerics. There you can precisely control that, make sure that your system is isolated from outside world. But I don't think you can go to, maybe right now you can go to large system size, but one of the very first papers verifying ETH, eigenstate thermalization hypotheses, using numerics is like very few sites or qubits, things like that, numerically. But maybe people.
For interacting system, yes.
Yeah.
I mean, it's what you can do. I mean, of course, for not interacting, you can always do more. But for interacting, no.
But again, in the numerics, I think it's all real space based. I haven't seen like k-space or momentum space thermalization.
Well, no, there are, yes, no. There are even in momentum space. I mean, indeed, I mean, I said I never worked, it's true, but I did some work with Lorenza in non-interacting systems in k-space. And we look at, you know, precisely thermalization, and what we notice is that thermalization in N of k you can find, but this doesn't mean that if you look at the correlation that is going to be thermalized. So I think that there are these kind of subtleties. Okay?
I see.
There are these kind of subtleties. So
correlation. Sorry, correlation in real space or in space?
No. This was in momentum space.
Oh, okay, I see.
So you said that you didn't know people doing momentum space, and then I say, yeah, it's not true that I never did anything on this field. But in particular, in momentum space, yes, we did.
I see, but it's not interacting.
It's not interacting, it's trivial, of course, because we were looking at, you know.
Yeah. I think, when I say I don't know about anything doing in k-space, I was referring to like interacting case.
Yeah, in interacting case is harder.
Yeah.
But I'm not sure that Marcos Rigol didn't do anything in momentum space.
Yeah.
I am not sure because I think that Rigol did some things maybe with hardcore bosons or things like that. I don't remember exactly, but I mean, I have some recollection that he could have done something along these lines in k-space. I mean, but I cannot guarantee.
The numerical paper I was referring to is Rigol's paper, but my recollection is it's only in real space. Maybe I think he did the section about k-space.
Yeah, I think he did more, but I cannot guarantee. As I said, it's not a field that, you know, I've been doing a lot. So I mean, very nice work.
Yeah, thank you for the questions. Yeah, they are very valid questions and concerns.
Yeah, no problem.
But as I said, I think we don't have a clear understanding. None of the people in the field has a very clear understanding. We're working towards it, but
no, that's a worth goal.
Patching together. Yeah.
Perfect, Suher. Thank you very much.
No, thank you. I mean, it was, and thank you very much for a great talk. It was really fantastic. I'll probably ask you quite a few questions tomorrow.
Okay. Thank you for the opportunity. Yeah.
No, come on.